Hey, nice to meet you. Can you run an algorithm in transistors? Why not? I'm gonna show you how. This is an intelligent automatic watt level controller algorithm. It's a simple program, simple logic. Today, we're gonna run this algorithm in transistors. Let's talk about it. In the digital world, a transistor is a binary switch and the fundamental building block of computer circuitry. It's a simple component, but sometimes simple things make big difference. The working of the transistor is easy. It either prevents or allows current to flow through, like a light switch on the wall. How does a switch make computing possible? Well, different combinations and arrangements of transistors make different kind of circuits. For instance, memories, microprocessors, microcontrollers, GPUs, integrated circuits, and many things. Do you know the Intel Core i9-12900K is made out of 2950 million transistors? It's not a joke. And you know the programs are literally a collection of mathematical operations in one form or another. The CPU knows how to run them. The computer doesn't construct the circuit for every computer program. It instructs the transistors how to act as per the computer program. And those in turn provide an output. So if we're gonna construct a circuit to run a specific algorithm, then there is no need for programming. It will run like a fixed logic unit. It will only do what it wanna do. Like a CPU is designed to run only a task. That kind of CPU doesn't exist, by the way, but consider this as an example. As a result, the circuit is faster, simple, stable, optimized, cost-effective, and we can call it discrete logic. And here it is. Inside this black box has a transistor logic circuit built out of 9 transistors, which cost about 1 cent per each. The total cost of the circuit is around $0.62. $0.62. Think about that. And the circuit is taking inputs from 2 float switches. I put one in the top and one in the bottom of the bowl to read the water level. And both are configured in active low mode, means if the float switch is on, the output goes low. When it's off, output will be high. High is equal to 1, low is equal to 0. That's how binary works. We're gonna feed these float switch signals to resistor transistor fixed logic unit of the circuit. I made that using 4 transistors. And I made a 1-bit memory using another 4 transistors. You know, without the memory, we can make an intelligence. And the output of the memory is driving another transistor, which is driving the relay. That is used to switch the pump on and off. Let's talk about how it works. Well, for simplicity, I made a block diagram for you. The main part of the circuit is the memory. It's a 1-bit memory, so we can hold a single bit binary value like 1 or 0 as long as you can until you reset or break the power. Because it's a volatile memory like the RAM of your computer, the memory has 2 outputs, Q and Q dash. Q is the actual output and the Q dash is just an inverted version of Q. For instance, if Q is 1, then Q dash is just the opposite of it, that is 0, right? And I put a switch to select the output Q and Q dash for a good reason to invert the logic. I'll try that in a moment. If we throw a logic 1 to the set input of the memory, it will set and hold 1. If we throw a logic 1 to the reset input of the memory, it will clear the memory, meaning it will back to 0 and hold 0. So actually we are using the resistor transistor logic unit to combine the inputs from this float switch and make a logic signal to set and reset the memory. And I figure out where we want to set or reset the memory. If we set the memory, it will turn on the pump. If we reset, it will turn off the pump. When do we want to set the memory? We want to set the memory when the water is low. If the water is low, both float switches are in the on position, so we get zeros from the float switch. Then, when do we want to reset the memory? We want to reset the memory when the water is full. If the water is full, both float switches are going to float. So, we get 1s from the float switch. So we have to set the memory when both inputs are 0 and reset the memory when the inputs are 1. Then I did some math for the circuit design and I did Boolean algebra SOP and I created this RTL circuit. At the transistor level, I created all the logic gates. If we're gonna run the same algorithm in an Arduino or any microcontrollers, this circuit will beat that in every scenario because it will finish the output within the time taken for a microcontroller fetching a single instruction. Take input, switch, boom, got the output. That's how fast it is. Now it's the time for the demo. Okay, actually I made this thing to solve a problem, and the problem is, see, we already have a barrel, but the water is very low for some season. So we take tap water. I want to collect the water to this barrel, but the force is not enough. If I put the hose a little bit high, see, it stopped. To solve this issue, collect the water with a short container and wait and waste all my fucking day and pour it into the barrel. So now I made this magic container. Everything is in place. Flip the embed logic switch, put the hose into the barrel. It will do the job for me. What you got from this? We just reverse the working by flipping that embed logic switch. Now it will take care of it. See, the exact algorithm is running on the transistor level.